Hi everyone, welcome to Differential Calculus. Today we explore lesson 4.9 applications of antiderivatives. This is the last lesson in differential calculus. We have example in physics, very useful. Let's take a look. Example number 1, a student wants to measure the height of a cliff. The student climbs on the top of the cliff and drops a stone. The stone hits the ground at a speed of 150 feet per second. Find the height of the cliff. Okay, so here come the cliff. It's stone. And that is the ground right here. We know a few things. We know that the stone is being dropped, meaning that the initial velocity is 0 feet per second. We also know another very cool information is the initial height with respect to the ground is the height of the cliff. Is height of the cliff. We also know the impact speed. (150 feet per second). Well, it be turned into velocity if you use the impact velocity. Then it would be, remember, velocity is a vector, so it has a direction. If we go down, it's negative 150 feet per second. Okay, according to the information, let ft be the position function of stone at time t. Then f prime t is velocity. F prime t is acceleration. The stone is dropped down, and the only acceleration is the gravity, the gravitational acceleration, which is negative 32 feet per second square. Okay, so we're going to begin from there. Begin from f prime t, and we use antiderivative to get the velocity and the position function. Very cool, huh? Okay. The antiderivative of the second derivative is the first derivative. So f prime t is negative 32 t plus c. And then we use initial velocity. It's 0 feet per second. So that is f prime of 0 is 0. 0 is negative 32 times 0 plus c. So c equal to 0. From there, we know that f prime t is negative 32 t. So f of t is negative 32 times t squared 2 plus c. And that gives us negative t squared plus c. Remember that negative 16 t squared that you used to see in the algebra textbook. That is how we get it, using gravitational acceleration and antiderivative. C is the height of the cliff, because that is the initial height. So this is the height of the cliff here. Or initial position, cliff height. Impact time. Well, that is when the velocity is negative 150 feet per second. We know velocity is negative 32 t equal negative 150. So t is 150 over 32 second. Okay. Once we have the impact time, then we know after this many seconds, from the impact time, we know that the position of the stone after 150 over 32 seconds is 0 feet, because it is on the ground. Position of the stone after 150 over 32 seconds, that would be f of 150 over 32 is equal to 0 feet. It's just 0. So we do the substitution and we solve for C. Negative 16 t is the 150 over 32 square plus C equal to 0. C is 16 times 150 over 32 square, which approximately equal to 351.56 feet. Example 2. A driver is in a rush and travels at 90 miles per hour on Highway 280 in the Bay Area. The driver sees an accident ahead. The driver stamps on the brake, producing a constant deceleration of 50 feet per second square until the car stops. Determine how far the car travels after braking. Let's sketch a picture so you can see what is going on. We have car right here, and it's been driving at 90 miles per hour. Easy to get a ticket. And at this time, apply the brake. We have a braking distance right here. And at the end, car stop. The braking distance, well, produced a constant deceleration. Deceleration is negative 50 feet per second square. So if ft is the position function, then at time t, then f prime t is the velocity. F second prime is acceleration. Well, in this case, we don't have acceleration, we have deceleration. Second derivative is negative 50. The antiderivative of the second derivative is the first derivative. So f prime t is negative 50t. Don't forget to plus c. To find c, we got to use the initial velocity. The velocity is 90 miles per hour though, so we have to convert it to feet per second. 90 miles per hour is 90 miles over 1 hour. And we can convert mile to feet by, notice that 1 mile is 5280 feet, and 1 hour is 3600 seconds. Work out the arithmetic. We have 132 feet per second. Okay, so that would be the substitution. Now let's sub it in and figure out C. F prime of 0 is 132. So we have a 132 equal negative 50 times 0 plus c. C is 132. So that gives us the velocity to be negative 50 t plus 132. Next step is we're gonna figure out the position of the car. Position is the antiderivative of the first derivative, which is negative 50 times t squared over 2 plus 132 t plus c, or negative 25 t squared plus 132 t plus c. To solve for c, we used initial braking distance, which is 0. So now f of 0 is equal to 0. 0 is equal to 0 plus c. So that means c is 0. And then from here, we have f of t to be negative 25 t squared plus 132 t. We need to use the fact that the car comes to a complete stop when the velocity is equal to 0. Time when car stop. That is when the velocity f prime t equal to 0, negative 50 t plus 132 equal to 0. So that tells us t is 132 over 50 seconds. And when we know the time the car stop, we know the braking distance. Braking distance after 132 over 50 seconds. That would be f of 132 over 50, which is negative 25 times 132 over 50 square plus 132 times 132 over 50, which is approximately 174.24 fit. Wow, it's too bad for the driver. It's going too fast. Cannot stop on time. Either that or the car is need an upgrade. It's a pretty dangerous braking distance. Thank you for watching. I hope you found the content useful. Please like and subscribe to help the channel growth. I will see you in integral calculus